Hey y'all, today we're going to talk about subatomic particles to answer the essential question, what are atoms made out of? So here I've got a helium atom, but what's going on underneath? All right, underneath all elements are made of three main particles, protons, neutrons, and electrons. All right, the protons and neutrons exist inside of the nucleus, which is the center of every atom. There's a different number of them depending on what atom you're talking about. Those protons I've colored here blue with a little plus symbol because these are positively charged particles, positive charge. All right. These neutrons here I've represented gray. They're neutral, so they have no charge, represented by this 0 here for 0 charge. And together, the protons and neutrons make up what we call the nucleons. Because they exist in the nucleus, that's where they get their stuff on. All right. Then lastly, we have the electrons, which are very small negatively charged particles that are found in electron orbitals outside of our nucleus. Okay, so those are the three main subatomic particles that we'll be talking about. Here is a table representation of some information about these particles, right? So here we've got the protons. They have a mass of what we call 1 atomic mass unit, which is a very small number of grams, but this just makes the math easier to call a proton as 1. Neutrons are also about 1 atomic mass unit, and then those electrons are about a 2,000th of an atomic mass unit. They're so much tinier and so much lighter than protons and neutrons. Okay? The charge of these particles, the proton is positive, the neutron is neutral, so no charge, 0 charge, and then the electrons are negative. They have that negative charge. We can find the protons in the nucleus and the neutrons in the nucleus. Remember, these are our nucleons. And then the electrons exist in electron orbitals outside of the nucleus. We can represent their symbols as such. Protons, P with a plus, neutrons, a lowercase n with a 0, and then electrons floating around about here we could represent with a lowercase e with a little negative symbol to show their negative charge. Okay, now don't memorize anything here, but I just want to show this because there's more to the subatomic world than just these three particles, but those are the only ones we're going to talk about moving forward. All right, but before we get too ahead of ourselves, we are going to start using the periodic table. So I wanted to be a little bit keen about two things that we're going to use, two vocab terms. First of all, the columns in the periodic table we're going to call groups or families. And the rows of the periodic table we're going to call periods. All right. Now the neat thing about the columns and the rows, or the groups, families, or periods, is every element in a group or a family has similar properties, and all of the atoms in a row also have some shared similarities. All right, just a little bit of vocab here. Now, the reason we're talking about how to read the periodic table is because the periodic table tells us important information about each of these atoms that we'll talk about. We can figure out the number of protons, neutrons, and electrons that an atom has. So you'll notice each square on the periodic table has an element, but also some numbers associated with it. The first number here is the proton number, which I'll call the atomic number, all right, in blue, which tells us how many protons an element has. So iron has 26 protons. If you add a proton, it becomes cobalt with 27. If you add a proton, it becomes nickel with 28. If you add another proton, it becomes copper with 29. Right? The number of protons determines the element that we have. All right? This will also be the number of electrons if an atom has no charge. The second number here is the atomic weight, which tells us how many nucleons, which again are the protons and neutrons, there are in the atom. You may be wondering why aren't the electrons added in? They have a 2,000th of an atomic mass unit that we should be keeping track of. And you're right, we should keep track of it, but electrons are so light, they basically add nothing to the atomic weight, so we just ignore them. All right, they're pretty much worthless when it comes to measuring their weight in the atom. Okay? So we want to do an example. Iron has 26 protons as shown by its proton number, and it has 56 total nucleons as shown by its atomic weight. All right. So using this formula here, the number of protons and number of neutrons added together give us the number of nucleons, which is the atomic weight. So if we know one of them, we can figure out the other. So 26 of iron's nucleons are protons, so the other 30 must be neutrons. So those 56 nucleons minus those 26 protons means iron has 30 neutrons. All right. So what happens if we change any of these subatomic particles? We change the number of them. When the number of protons changes, we get different elements. So if you took iron and you added one more proton, it would become cobalt. You add another proton, it becomes nickel. You add another proton, it becomes copper. You add another proton, it becomes zinc. The number of protons determines what element you're talking about. When the number of neutrons changes, we get something called an isotope. All right? An isotope, it's the exact same element, it's just a little heavier or a little bit lighter, depending on if you added more neutrons or took some away. Right? When the number of electrons changes, we get ions. We have the exact same element still, but now it's an ion with a charge. And an atom's charge can be calculated as follows. We can have the number of protons minus the number of electrons is equal to the charge. That's because protons are positive and electrons are negative, so if we subtract the two, we can find the difference in our charges. All right. A cation is an atom with a positive charge. You can think cats have paws, if that helps. A positive charge because they have lost electrons. Anions are atoms with a negative charge because they have gained electrons. Okay. Now there's one piece of information down here that we won't mention for a while, but atoms will usually gain or lose their electrons to try and get 8 electrons in their outermost level. That's just something for now that we won't talk about for a while. Okay, so let's talk a little bit more about calculating charge. So we're talking about these ions and changing the number of electrons. Okay, we can take the number of protons minus the number of electrons to find that charge. So let's say we have 1 proton and 1 electron. All right, one proton has a charge of +1, 1 electron has a charge of -1, so overall the charge is 0. Okay, that's not too bad. What if we had 2 protons and 1 electron? Well, 2 protons have a charge of +2 overall, and 1 electron has a charge of -1, so overall the charge is +1, because we have one more plus charge than we do minus charges. All right, what if we had 3 protons and 3 electrons? Well, 3 protons has an overall charge of +3, and 3 electrons have an overall charge of -3, so overall our charge is 0. We have the same number of positive charges as we do negative charges. Well, let's make this a little bit more complicated. Let's say we had something crazy, like a whole ton of protons and a whole ton of electrons. So we have 16 protons, that gives us a charge of +16, and we have 18 electrons, that gives us a charge of -18. So we have 2 more electrons than we do protons, so overall the charge has got to be -2. All right, and we can show this off if we just cancel them out. We're left with 2 electrons, 2 negative charges left over. So the last topic we'll discuss here is nuclear symbols, which is just a neat, clean way of representing all the information we're talking about. So this sodium ion we have here, I know it's an ion because it's got a positive charge. This sodium ion is just an element of sodium, and we write its chemical symbol. The atomic number we'll write in the bottom left, so sodium does have 11 protons, so that's also its proton number. The atomic weight is written in the top left, so we know protons plus neutrons here. This is the weight of this sodium atom, so it's got 12 neutrons in addition to its 11 protons. Okay, and then lastly we have the charge, which is written in the top right if we have one. In this case we have a positive charge. If we know protons minus electrons give us a charge, we have a charge of +1, which means we have one more proton than electrons. So we have 11 protons and 10 electrons in this case. All right, let's go through some examples. In this case, we're looking at hydrogen, which has 3 natural isotopes, hydrogen 1, hydrogen 2, and hydrogen 3. If you're interested, the names are protium, deuterium, and tritium. All right, so for this first hydrogen atom, it's got 1 electron swirling around, it's got 1 proton, it's got 0 neutrons. So its nuclear symbol here would be 1 for its proton number, 1 for its protons plus neutrons, and there's no charge, so we don't write 1. This second hydrogen atom now has a neutron, okay? So we'd write 1 again for the proton number, because it's still hydrogen, and then 2 because 1 proton plus 1 neutron gives us 2 for our atomic weight. Then for this last one here, all right, and you'll notice this one is a little bit unhappy. This is a radioactive isotope of hydrogen. We have 2 neutrons and 1 proton, so our overall atomic weight is 3, but our proton number stays the same at 1. All right. Now let's look at hydrogen's different charges. It has 3 natural charges. You'll find -1, 0, and +1. So for this first atom here, we have 1 proton and 2 electrons. So this is hydrogen minus. This is an anion. This middle middle atom here has 1 proton and 1 electron, so the charge would be neutral, so we don't have to write it. And then this is if hydrogen loses all of its electrons, it's actually just a free-floating proton. And in this case, it's just a proton with a positive charge. Okay? All right, but let's look at something a little bit more complicated. Now we're looking at carbon and its 3 natural isotopes. You're made of quite a bit of carbon. Here on the far left, we have 6 protons and 6 neutrons and 6 electrons. So the way we'd write that nuclear symbol, 6 for our proton number, 12 for our atomic weight, because it's protons plus neutrons, and then no charge, so we don't have to write one. For this middle atom here, we have 6 protons and 7 neutrons, so our overall atomic weight is 13. And then for this last one, we have 6 protons and 8 neutrons, so our overall atomic weight would be 14. And this one is also a radioactive isotope, just like that tritium hydrogen-3 we looked at. Okay, so I'm going to walk you what some of these example problems will look like from your packet. So I will be giving you some information, and you have to figure out the rest and fill in the table, which you should be able to do if you know how to read your nuclear symbols. Starting with this first one, this is nitrogen. Its atomic number is 7, which is the number of protons, and its atomic weight is 14, which I can fill in there. So I get proton number 7, atomic weight of 14. If I want to find out the number of neutrons, I take the atomic weight minus the number of protons, so that gives me 7 neutrons. Then lastly, if I want to know the number of electrons, I have to look to see, do I have a charge? Nope, there's no charge, which means for every positive charge I have, I should have a negative charge. If I have 7 protons, 7 positive charges, I should see 7 electrons as well. For this next one, we've got zinc. Now, if we look on our periodic table, which would be handy to have for this, zinc is element number 30, which means that's its proton number, and I can fill that in immediately. Then I know its atomic weight is 65, because that's given to me. All right, that atomic weight is up here. Then the number of neutrons is as easy as taking 65 minus 30, which gives us 35 neutrons. And then it also was nice enough to give us the number of electrons, which is the same as the number of protons, which means there's no charge. Nice. All right, now lithium here is element number 3. So I already know that, but first let's just write down the information that we got. All right, we got that 3 proton number, which I just talked about, and that 7 atomic weight, which is given to us. Then if I want the number of neutrons, that's not so bad. 7 minus 3 is 4. Then lastly, I got to be careful here. I only have 2 electrons and 3 protons. So our 3 positive protons minus our 2 negative electrons gives us an overall charge of +1. All right. Next, we got this one here. Well, it gives us protons and neutrons. So let's just add those together to get the atomic weight. All right. So 16 plus 17 gives us an atomic weight of 33. Then, if I look at the proton number, right, I'm over here. This is sulfur right here, which is element number 16. So I know it's sulfur, so I can write S for that. Proton number 16, atomic weight 33. And then the charge, I take my proton number of 16 minus my electron number of 18 to give us the 2 minus charge there. Then this last one may look a little tricky, but it's actually given us all the information that we need. It's got a +4 charge, whatever this thing is, and we've got 21 electrons. So that means I have to have 25 protons in order for that charge to work out. And then from there, I've got my atomic weight of 55, so I can know that my number of neutrons is 30. And then to figure out the symbol, I just have to look at what element is number 25 on the table, and it turns out it's manganese. So Mn is the symbol. We write 25 for the atomic number and 55 for the atomic weight. Nice. Hey, that's all. So as usual, I got my song recommendation. The picture I chose for today was actually an image taken of hydrogen atoms using a praseodymium orthoscandate crystal in a very large microscope. But this is a little bit of a different microscope. It uses ptychography in order to image very small atoms. So take the checkpoint quiz when you're ready, but otherwise, see you later, chemists.